Okay, I wanted to start by clarifying something that we were going over just at the end of class, and I kind of rushed through it, so I didn't quite say it the way that I should have said it. So if we look at the shielding on an Srp electron, remember this is the one that we're saying how much shielding does this particular electron get. We have these rules that we went through, 0.35 for the same group, and that means that it's in the parentheses with that particular electron. And then 0.85 for anything that has one less for the principal quantum number, and then 1 for anything that is further to the left on the line or deeper into the core. And then on the D and the F, within the same group, it's going to have a 0.35, just like for the S and the P electrons. But for the S and the P, that means that both kinds of electrons, both S and P, shield at 0.35. But we don't really have to consider anything that's outside of that parentheses because there aren't any others that have the same N level. For a D electron, the only thing inside the parentheses is a D electron. So when we say 0.35 in the same group, we mean other D electrons at the same energy level. Anything that is to the left of that on the line up above. So if I'm looking at the 3D, everything to the left of it is going to shield a full 100%. So even though the 3S and the 3P have the same energy level, that's going to be a shielding strength of 1. Whereas we saw with the S electrons, we had a 0.85 when it was N-1. We don't have that for the N-1 for the 2S or the 2P, but we don't even have that for the same energy level. So the 3S and the 3P are going to shield at a full 1. So that's an important thing to remember. And then another thing to point out is that you are sometimes going to have situations where you might have electrons in higher orbitals. Like, for example, you might have a 5S electron, but not have any 4D or 4F. Or you might have 5P electrons, in which case you would have the 4D, but you wouldn't have the 4F. So on this line, you might have things that are missing. Okay, so now a word about using the paper that I gave you. I'm going to stop sharing for just a minute so that you can see this paper. All right, so if I am looking at a 3D electron, and I want to know how much shielding happens from the other electrons. Well, the 3D, those are generally going to be the outside electrons in my first row of transition metals. So scandium, titanium, vanadium. And so that means that I have an electron configuration that goes through the 1s, 2s and 2p, 3s and 3p, but it also has 4s electrons. So that's in this gray area for the 3D. If I go over, that's gray. We're not going to count that. That's going to be 0 shielding because that's further out, okay? And I would look at all of my 3D electrons for that particular one. So the other ones in the same 3D orbital would shield at 0.35. And then you notice all of these are full 100% shielding, okay? But if I go down one and I'm looking at the 4S or the 4P, suddenly these things that were shielding at 100% for the D are only shielding at 85%, 0.85 for the S. Okay, so we have a change in how much those lower level electrons are shielding. Okay, we are going to look at how to determine Slater's rules or how to use Slater's rules to determine the shielding and the effective nuclear charge. So we use the example of aluminum in class today. What I want to do is take a look at some of the heavier elements and how the S versus the D versus the P electrons might have different kinds of shielding. So let's take a look at vanadium. Oops. I'm going to do in vanadium, and let's take a look at the 4s electron in vanadium. So the first thing we want to do is write out the electron configuration. And I'm going to put spaces in between the different groups so that we know how we can apply those. So for vanadium, it is, and I can't superscript on here, but it is 1s2, and then we have 2s2, 2p6, and then we have 3s2, 3p6, and then we have 3d. So those are all in the same energy level. They're in the third energy level. And, but we have them separated into different groups because the D and the P and the S have different levels of shielding. And then we have 4s2, and that is our outside. So if we look at a periodic table, vanadium is the third element in the 3D section. So there are 3D electrons. So these are the outermost electrons, and these are the core electrons. And we are going to be interested in the 4s electron here. Okay, so the first thing I want to do is I want to know how many electrons are going to be doing the shielding, and then I want to know how much shielding each of those apply to the 4s. So remember, how much something shields depends not only on where it is, but where it is relative to the electron in question. So if you are using your chart, our 4s electron is what we're going to find on the side here. So we're going to come down to about here to find the 4s, and we can see the numbers here. We'll double check those in just a minute. Okay, so get my text box back here. We have two 1s electrons, and then we have 8 in the group that is the 2s and the 2p. We similarly have 8 in the group that is 3s and 3p. And then we have 3 electrons in the d orbital. And then there are 2 electrons in this s orbital, but the electron can't shield itself. So only 1 electron is going to be counted for the shielding. So this is, write this to the side, the number of electrons. All right, now down below that, we're going to do the shielding for each of these. How much do each of those electrons shield the 4s electron? So anything that has an n value, this first coefficient that is 2 or more than 2 less than that of the electron in question. So we're looking at something that is either a 1 or a 2. That's going to have a complete shielding. So 100% for the 1s, 100% for the 2s and the 2p. And then down at the next energy level, the one that's right below the electron in question, the 4s, that's where we are at 0.85. And that's true whether we have a d electron or an s or a p. So they all shield the same amount according to Slater. And then within that same orbital or type of orbital, we are going to have only 0.35. So the second s electron in the orbital will only shield by 0.35. So we're going to multiply these numbers, the 2 times the 1, the 8 times 1, 8 times 0.85. We're going to multiply those and add all that up. And so we'll see what our shielding is. And I'm going to pause. All right, so for this first 2 groups, we have a value of 10 for the shielding. Then for the next 2 groups, we have 11 times the 0.85, and that's going to give us 9.35 for our shielding. And then we're finally going to have 0.35. I'm going to put a plus in here as well. So when we add all of that up, we get 19.7. Okay, now this tells us how much of the nuclear charge is shielded. So we need to compare that to what the actual nuclear charge is. So we are going to say that Z is equal to, for vanadium, 23, and Z star is equal to S minus Z, and that is equal to 23 minus 19.7. And so that S electron feels a charge of 3.3. All right, so it's more strongly attracted than the electrons in the alkali metal group would be, and that makes a lot of sense. Let's take a look at what would happen if instead of 4s, we were looking at the 3D. How does the story change? Okay, so we still have the same number of electrons for most of the groups, but this end is going to change here. So I'm going to copy our grouping here down below. I'm going to try and copy it. Maybe I'm not. I'm just going to move it down here. Okay. So now we are going to do our number of electrons in each of these and see how that changes a little bit. So the first set is all going to be the same. I'm just going to say that's 10 for those first two. And then we have 8 for this group. But when we get to the 3D, since the electron in question is a 3D electron, we're only going to count 2 of those, so 1 less. And when we get to the 4s, there are 2 of those. We're going to count both of those. So now we want to know how much shielding is in place for each of these. So we have full shielding for this first one, and our rule for the 3Ds. So again, we are looking at our chart here, and we're going to look at the 3D here. So our rule for the 3D is that everything that comes before it shields for the full amount. So these are going to shield by 1. And then within the same group, we're still going to have that 0.35. What about this 4s? Well, the 4s is outside of that, so that shielding is going to be 0. So our math then becomes S is equal to 10 plus 8 plus 0.7 plus 0. And that gives us 18.7. And the Z effective for the 3D electron is equal to 23 minus 18.7. And that is going to be equal to 4.3. So what this tells us then is that the D electron is held a little bit more tightly than the S electron is. So when we are trying to remove an electron from the vanadium atom, it's going to remove the one that feels less of the nuclear charge. So remember that the S electron feels 3.3, the D electron feels 4.3, and so because the S electron feels less, it's going to be ionized first. All right, so let's take a second to compare the math that we did with this chart here. So we said that these, let's look at the bottom here. My spotlight. We said that these electrons in the 1s2, 2s2, and 2p2 all shielded at a value of 1 when we were looking at the D electron. So remember, we were keeping in mind this D electron here. So if I go down to the 3D electron, the 1s here has a value of 1. The 2s and 2p also have a value of 1. Okay, but or rather, then if I go on to the 3s and the 3p, they also have a value of 1 for the D electron. Okay, now if the electron in question were the 4s, that would be a different story. It would be this 0.85. That's what we saw up above. But since we're looking at the D electron, it's a value of 1. Okay. And then within the 3D, within that same grouping, we have the 0.35. All right, so let's look at another example. This time we're going to look at chlorine, but we're going to compare it to chloride. So we're going to see how changing the number of electrons is going to affect the shielding and the effective nuclear charge. So I've written out the electron configuration for the chlorine here. And what I'm going to do is put the number of electrons. So we have, click in here, 2 electrons in the 1s. We have 8 electrons in the energy level 2, and we have 7 electrons in energy level 3. Then we are going to determine how much shielding occurs from each of these. So for the at 1s, that is 2 energy levels down, so we get a full shield from that. 1 energy level down at the n equals 2, we get 0.85, and within the same type of orbital, we have 0.35. So that is the amount of shielding. Now, remember that we're not going to count all of the electrons in the S and the P, because the 1p that we are looking at is going to be different, or is not going to shield itself. So there are 6 shielding electrons. Okay, so then we're just going to multiply those numbers. So our total shielding is going to be equal to 2 plus, calculator real quick, 6.8 plus 2.1. And that is going to give us a total of 10.9. And that is going to give us an effective nuclear charge of, well, remember, we're going to have to take Z for chlorine, which is 17. That's its atomic number, minus the 10.9. And that's going to give us 5.1. Okay, so that p electron, any one of the p electrons, or the 3s electrons, any one of them is going to feel a nuclear charge of 5.1. And this is why chlorine as an atom is so small as it's being attracted in. All right, so how does that story change when we have a chloride ion, and how do we expect that to change the size or the radius of that particular ion? So situation looks pretty similar here for our number of electrons. We have 2 electrons in the 1s, 8 electrons in level 2, but now we have 8 electrons in level 3, 7 of which are going to do our shielding. So the shielding is still going to stay the same, 1 for that first level, 0.85 for the second level, and 0.35 for the third level. So our total shielding is going to look similar. We're going to have 2 plus 6.8, but then that last number, instead of being a 2.1, is going to be a 2.45. Did something wrong there. Sorry, 11. That last number is going to be 11.25. Okay, how does this affect our nuclear charge? Z star, or the effective nuclear charge, is going to be 17, the atomic number, minus the 11.25, which is going to be equal to 5.75. I did something wrong there. This is 6.1. Okay, so if we compare the attraction of the nucleus, in this case, we have a 6.1 effective nuclear charge, which is why chlorine is so small, because it's got a very high effective nuclear charge, whereas the chloride ion has somewhat less. And so with less attraction for each individual electron, they all spread out just a little bit, and we have a larger ion. Okay, let's look for a second at how what we did here compares to our chart. So for the chlorine, we had the 1s electrons. We're going to shield by 1 when I'm looking at a 3p. So I'm going to look on this chart, go down to the 3p, this third row here, and I'm going to see in that first column, the 1s shield a full 100%. Then the next group is the 2s and the 2p. So as I slide over, that's only shielding at 0.85. Okay, so that's what I wrote down on the screen here. And then my last group, where the valence electron is the 3s, 3p. And if I come down, that is 0.35, and that's where this falls on here. So you can see how you can use that chart if it is easier to just kind of use this as a reference rather than memorizing the rules and going back to those. All right, so let's look at something a little bit further down on the periodic table. Here we're going right to the question, what is the effective nuclear charge? So that means we're going to find Z star, but we're going to need to find the shielding first. And we're looking at a 5s electron on rubidium. So rubidium is an alkaline earth or alkali earth metal. And so it only has 1 electron in that outside shell. So we're just looking at the shielding on that 1 electron. So I've written out the electron configuration here according to the appropriate grouping. And what I've done here is I've included the 4d0 here, just to indicate that if there were d electrons, they would be included before the 5, but this 0 indicates that there aren't any of them. Okay, and then down below, I've put sort of a pseudo-noble gas configuration, and we'll look at how that's similar. And if it's something you are interested in doing, it can save you a little bit of time. Okay, so we want to figure out how many of each of these electrons we have. So just going across, 2 in this group, 8 in this group, 8 in this group, 10 here, 8 here, 0d electrons. And then remember, we're going to subtract 1 for the electron level that we're in. So since there's only 1 electron, there's nothing else in the 5s orbital or even a 5p orbital that can shield that one. So that one is also going to be 0. Then we are going to put how much shielding each of these will do. So this is an n equals 5 electron. My spotlight back, n equals 5 electron. And so that means that we're going to have a decrease for the level 4 electrons, but once n is equal to 3, where it's 2 less than the 5, all of this stuff with n equals 1 to 3, all of that is going to be a full 1 or 100% shielding. So let's get back to our picture here. So this one will be 1, this one will be 1, this one will be 1, this one will be 1. And then when we get to this group, 4 is going to be a little bit less than the 4 is going to be a little bit less than for the level 5. The shielding is going to be a little bit less than the core electrons. So we're going to have a 0.85 here. And then we're not going to have anything out here. Now, if we were to include the 4D, it would also be 0.85 because it is in the same energy level. They are, so the 4D is in the same energy level with this group. And so it would also be 0.85. And if I had this one, it would be 0.35. But I'm not going to include those because there are no electrons there. All right, so we can multiply that across. What I want to do is look at this sort of pseudo-noble gas configuration. Now, instead of writing the previous noble gas, which would be krypton, I went back 2, so I used argon, and that was so that I could write out the configuration for the n-1, because we know that that's a little bit different than the deeper core. So when I do this, I can kind of combine things a little bit easier, not have to separate all of these things that are equal to 1. So doing this, I have 18 electrons that are part of the argon core, and then 10 here, 8 here, and then I'm not going to count my s electron. So I'm going to end up with the same numbers because when I multiply, I'm going to multiply this first group by 1, and that includes all of these electrons here. 2 plus 8 plus 8 is 18. So all of those are getting multiplied by 1. And then this set is also going to be multiplied by 1 because it's level 3, and then I'm going to do the 0.85, and I have 0. So I have 18 plus 10 is 28, and then my 8 times 8.5. I'm sorry, 8 times 0.85. So that gives me a total of 34.8. And so if you did the same thing for the set up above, you'd end up with the same thing. So remember that we are ultimately not looking for the shielding, but for Z effective, or the effective nuclear charge. That is going to be equal to Z minus S. So for rubidium, that is element 37. So it has 37 protons, and we're going to subtract off the 34.8. And we end up with a 2.2 effective nuclear charge. So we might ask ourselves, well, why did we fill that 5s orbital, or why did we put the electron in the 5s orbital instead of the 4d orbital? Logically, it seems like it would come first. So let's take a look at what would happen for the effective nuclear charge for that 4d. So I've written out the electron configuration down below, and you can see the first part is all pretty much the same, but I've got 4d1 and 5s0. So I've taken this S electron and moved it into the D. And we want to know what kind of shielding and effective nuclear charge did we see there. So our numbers are going to look pretty similar for how many are in each orbital. I'm going to again say, okay, all of these up to the 3p6, there are 18 of those. That's argon. And then I have 10 here. I have 8, so everything is the same there, but now I have the d electron here. But again, it's not shielding itself, so I'm not going to count it, and I'm not going to count the s electron because there aren't any. Okay, so this makes this look a lot like what was done up above, and so you might think, well, the shielding ought to be the same, but our rules for d electrons versus s electrons are a little bit different. So let's look at this next row. All of these electrons that are in the argon core, they get shielded by 1. And we said that same is true for those d electrons. The s and p electrons also shield at 100%. Even though they're the same energy level, they are to the left of the d. And that's why it's significant that we separated out the d electrons from that same group as the s and the p electrons. So we get full shielding there instead of the 0.85 shielding. And then the others are just zeros. So this makes our math pretty easy. When we add up all of the shielding there, S is going to be equal to 36. And that means Z effective is going to be equal to Z minus S, which is equal to 37 minus 36, which is equal to 1. So what does that tell us? That tells us that in the d orbital, the electron sees a nucleus of a positive 1 charge, but in the s orbital, it sees a nucleus of a positive 2.2 charge. So it is more strongly attracted to the nucleus when it is in the s orbital. That is why we fill that s orbital first. All right, one last time, I want to look at how we can use this chart to come up with these numbers. So let's look at this bottom part here where these numbers have come from. If I'm looking at a 4d electron, Julie, let's look at the top first. Let's look at the 5s electron. So going to the 5s, I go all the way down here. This is where the 5s is. And I can see that I have 1s going across for the first few groupings. So that's all the way up to the 3D. I'm going to have 1s for that. And that is what was applied here. All of the 1s, 2s, 2p, 3s, 3p, and then also this group of 3d. Those have 1. Then my next group over, I said was 0.85. So looking at where my 5s is here and going over to where the 4s and 4p are, I see 0.85. Okay. Now, if I had any 4ds, they would also be 0.85, but I don't have any 4ds. Same with the 4fs, I don't have any of those. So then I have the 0.35, which is my last group, but since there was only 1 electron in that case, I didn't count that.